Hello, hello. This is part 2 on chapter 24, organic chemistry. The homework is posted, and I should mention it is not from the book. So there's some lovely Word documents that you can, I would still advise printing off and then hand writing on top of them, or you could just write on different sheets of paper. But there are some drawing components of making some pretty Lewis structures that are specifically organic. But that's up to you how you want to do that. To start, we talked about alkanes the other day, and we said they are saturated hydrocarbons that have only carbon and hydrogen in all single bonds. And alkenes, instead of anes, are unsaturated. And so, what makes them unsaturated is they have at least one double bond. And to signify that it has double bonds, we're going to use the suffix "ene." So instead of things like ethane or butane, will have butene and ethene. The general formula will be for every carbon, it is H2N. So instead of 2N plus 2, it's just 2N. Now, I do need to mention this is assuming there's only one double bond, because if there happens to be multiple double bonds, then this can change to 2N minus 2 or 2N minus 4. For every double bond or degree of unsaturation, you lose another 2 hydrogens. So when we name this thing, we're going to use ene, but we're also going to use di and tri to specify how many double bonds there are, very similar or the same for substituents. So here we would still start by counting 1, 2, 3, 4. This is but for 4 carbons, but instead of butane, it's butene. And to signify whether the double bonds between the first and second, or second to third, or third to fourth, we're going to say it is 1 butene. So the number tells you where the double bond starts. And so we're not going to put 2 butene, or we don't even have to say 1 to 2. Just the 1 would tell us it's going to go from 1 to 2. Over here, we have 1, 3 butadiene. So that prefix di tells us there's 2, and it starts at carbon 1 and carbon 3. Now, we talked about this last semester, that anytime you have double bonds, they have what are called pi bonds, where it overlaps electron density above and below, and that prevents rotation across this bond. And so if these were alkanes with single sigma bonds, then whether you put these, like the chlorine on top or bottom, wouldn't matter, and they would be the same thing because they could rotate. But now this produces geometric isomers, also known, this specifically, as diastereomers. So stereo refers to in space. And so again, isomer, or same structure, but different arrangement. And so here we have the cis. Oh, there's a bell. That means something. I don't know. Let's see. It's 11:23 on a Wednesday. So I think that's the end of 4th period. Yep, 4th period is over. Just think to yourself, where would I be on a Wednesday at 4th period? Somewhere thinking about lunch. It's okay. Anyway, so if the larger R group, and R here you're going to see R a lot later in this chapter, and R just stands for the rest. So in this case, these are chlorines, but it could be a longer chain, or it could be a bromine, or any other substituent or alkyl group. And so if the larger of the R's are on the same side of the double bond, then this is what we call the cis configuration. So this is cis dichloroethylene. Eth, because there's only 2 carbons, ene, because there's a double bond. And often, if there's only 2 carbons and there's a double bond, you wouldn't have to say 1 ethylene, because there's only one spot it could be. But dichloro, so that there's 2 separate chlorines. And you could technically also throw in 1, 2 to tell you that they're out on 2 separate carbons. But the fact that it's cis tells you they have to be on 2 opposite carbons. If it was not cis, if they were both on 1, if these chlorines were both on, if this was 1,1 dichloro, then it couldn't be cis, and it wouldn't be a geometric isomer. So if they're on opposite sides, this is called the trans configuration. So where the larger R groups are on opposite sides, so across the pi bond. Again, these are two distinct isomers. They have different chemical properties. Again, here's looking at a few other ones. Here's malic acid and fumaric acid. These are parts of the TCA cycle. In olive oil, you'll find oleic acid, which has a cis conformation, where oleic acid is the trans. Again, so it looks like a pretty small change, just kind of a twist, but it does change the chemical properties. Probably the biggest thing most people know about trans is trans fats. And so when you hear trans fats, what's notable about them is if you look at this oleic acid, which is a fatty acid, in this trans, notice how straight it is, where the cis configuration has this kink. So when you have very, very straight, long, unkinked fatty acids, well, they pack together very tightly, leading to stronger London dispersion forces, increasing their melting points. Whereas if you think of olive oil has a bunch of unsaturated cis oleic acid, and that branching it doesn't allow them to couple as closely together. It makes them more dispersed. It lowers the melting point, and it's more likely to be a liquid and have lower melting points. And that's a good thing, because your body, they're less likely to form plaques and build up and clog arteries and fun things like that. So saturated fats without any double bonds have this linear structure, or kind of unbranched structure, but your body is at least able to break them down. Trans unsaturated is also linear, like it doesn't kink, but your body has a much greater time breaking them down, and so they're generally considered bad for you. Now, another neat place this comes up is vision. The way you're able to see your screen right now is through a cis-trans isomerization, where this word means you convert one isomer to another. So anytime a photon of light hits your eyes, hits your retina, you have these proteins called opsins that are absorbing the light. Now, the way they detect it and send a signal to your brain is if it hits the right type, if the right wavelength hits. Here, notice this is a big protein, and it has this little retinol, which is a part of a vitamin. It has a cis configuration. Well, if light hits it, it isomerizes to the trans, and this bulky part comes out of this protein, and that eventually sends the signal to your through the nervous system to your brain, saying, "Hey, I'm seeing light of this particular color." And so as soon as that happens, it isomerizes back, and it can happen millions and millions of times in a second. But you have billions of these opsin proteins that are all undergoing isomerization very quickly as soon as light hits it. Another place where we see this come up is ethylene, not the isomerization, but just another fun fact about alkenes. So you might know this, that if you want to make your bananas ripen, you keep them together. So ethylene is a plant hormone, and it helps them to ripen. And so sometimes if you keep your bananas in a paper sack, and kind of as they release it, keep those concentrations up, they'll ripen much faster. Ethylene is also going to come up in the next video when we talk about making plastics, like the ones you'd have in a soda water bottle or plastic baggie or all sorts of things. Then ethylene is kind of the fundamental base unit, and we use 120 megatons per year. That's a lot of this stuff. So now we would like to try and give some names to this stuff. So here's where I want you to practice it, and then I will tell you the name. So go ahead and hit pause and try to name these things. So go ahead and pause right now. Okay, and now we're back. I'm hoping you paused. So we want to name these things. So again, just like before, we're going to count carbons to find the longest chain. And we do also have to include any double bonds, and we want to give the double bond the lowest number. So instead of counting here, 1, 2, 3, 4, this is going to be carbon 1. So carbon 1, 2, 3, 4. And so this is butene, and because it's starts at carbon 1, it's 1-butene. And because we also have a bromine on carbon 1, it's going to be 1-bromo. And also because we can point out that the larger of bromine versus hydrogen, and this is the ethyl group over hydrogen. Again, not that we were going to call this ethyl, but because the larger things are on the same side, we're going to call this I meant to do a cis. There we go. Oh, I want that to go away. Go away. This is the cis configuration. So 1 to 4, 1-butene, cis 1-butene, 1-bromo. On this other one, we have 1, 2, 3, 4, 5, and it technically wouldn't matter which side we start at. So this is 1, 2, 3, 4, 1-4 pentadiene. And then here's a substituent. So if we have an NH2 group, what is that called? It's not nitro. Nitro's NO2. This is an amino group. And so since it's at the third carbon, this is 3-amino 1,4 pentadiene. Don't you just feel smart saying these words? Try saying them out loud. Use it in a sentence sometime today, and people are going to be like, oh, wow, you're smart. And yeah, then you could say, oh, it's no big deal. It's just organic chemistry. Now, on this one, I wanted this example to point out there are neither cis or trans. So if on either side you have identical things like 2 hydrogens on this side, 2 hydrogens on that side, there is no cis or trans. So this one has an isomer. If you were to switch the bromine and hydrogen, that would be 1-bromo trans 1-1-butene, but it's not. Again, as I said in the last video, we're not going to focus a ton on chemical reactions. There's like a whole semester of organic chemistry you could take talking about that, or maybe years. But what we could do is take something like an alkane, like ethane, and catalyze it into ethylene, and this process is known as cracking. So it's the general process. There's usually distillation involved in this as well, but you can break things down into smaller hydrocarbons. Anytime you form double bonds, if we were to go through, these are technically redox. If we were to go through and look up oxidation numbers, we would find that the carbons get oxidized as they lose hydrogen. Again, when we get in the next video, when we start talking about plastics, and ethylene is going to be one of the main players there. Addition reactions are going to be very common, where if you have a double bond, you can then easily add something polar like HBr, and it's addition because here's hydrogen added to the left carbon, bromine added to the right carbon. And there's what that looks like. Here we have, if you're breaking a double bond, it ends up being the carbons get reduced. The more hydrogens a carbon has, the more reduced it is. Or here's another addition where instead of HBr, we're adding bromine, and it's adding it to both sides. So again, I put the orange box because you're not going to have to know the different types. Here's another way of looking at this, or here's how we would tell. So here we have a vinyl group, or a propene, and HBr, and again, it's polar. This is, if you ever take organic chemistry in college, you'll talk about the Markovnikov rule. And what it tells you is, how would you decide whether the bromine should be added to this right carbon or the left carbon? So this is showing both. Do you get 1-bromopropane? Do you get 2-bromopropane? Is it a mixture? And Markovnikov's rule tells us whenever you, and go ahead and use this word. Well, it's actually a name, Markovnikov. So whenever you add something polar, the positive component, in this case hydrogen, is going to get added to the carbon that already has the most hydrogens. So if this carbon has more hydrogens than these, that's where this other hydrogen is going to go. So bromine gets added here. Again, there's a whole lot of rules when it comes to organic reactions, so we're going to kind of just stay away from that. We're mostly just, we're not looking for super in depth. We just want to get slightly acquainted with organic chemistry. Now, after alkenes, we have alkynes. This is where you can have triple bonds. So if there's one triple bond, the formula will be CnH2n minus 2. But again, this could change. It could be less than minus 2, like minus 4 or 6 if there's more double bonds or triple bonds. And here you'll see yne, Y-N-E. Now, if we're talking about biochemistry or biology, then triple bonds are pretty rare. You're not going to see them come up. So here we're talking more about synthetic hydrocarbons. So here we have 1, 2, 3, 4. So that's bute. And because the triple bonds on the first carbon, we have one butene. But here between the second and third, it's 2 butene. Here we're looking at acetylene. So sadly, we're not going to do this one. This would normally be a Fire Friday this spring. But calcium carbide in water, carbide is a polyatomic ion between two carbons that has a triple bond and a net -2 charge. If you add it to water, you get acetylene, which you can draw the Lewis structure of this. There's a triple bond, and then that is readily combustible, and you can do stuff with that. Here's a good video you should watch that just kind of reviews alkenes and alkynes. Now, that leaves us with the and those were the aliphatics. Now we have the aromatic. So aromatic refers to structures that have, it doesn't necessarily have to have a ring. All of our examples will, but here is a benzene ring. I've shown this to you many times before. We talked about how this thing has resonance, so you could write the Lewis structure either way, but in reality, it's more of a hybrid. And in organic chemistry, it's common to just draw a circle to show that the double bond is delocalized throughout. So we briefly talked about molecular orbital theory, and you don't have to know those theories. Just the idea is that these extra electrons are more stable or more delocalized. It's not single, double. All of these bonds are equal. Now, these come up a lot in organic chemistry. And one rule of thumb is that if you can have a molecule with aromaticity, an aromatic component, it actually happens to be more stable. There's just a thing. You can click on this link to look at a bunch of different aromatic compounds, but it's often going to be served as a base or itself a substituent. So here we have the aromatic ring. Again, by itself, we call this benzene, and it itself is an industrial solvent. It's used to dissolve nonpolar stuff. You can also find small amounts of it in gasoline, only about 1% because it's naturally found in crude oil. And again, that word aromatic, if you knew the word aromatic, you normally think of like, oh, pleasantly smelling. And that's originally why it was called aromatic. Is because if chemicals had these rings, they tended to be more volatile, hence you could smell them more easily. So if you ever spill a little gasoline, what you're probably smelling is mostly the benzene because it evaporates much faster. But again, here we have phenol has what's going to be called a hydroxyl group attached to it. TNT. So again, we can take this as a base and make all sorts of things from plastics, different drugs, different what are they called? Dyes. A lot of chemicals, organic chemicals that have color, like in food coloring, they're going to have these aromatic rings. So this is TNT, trinitrotoluene. So toluene, if you got rid of the nitro groups, then this is toluene. But then 1, 2, 3 nitro groups makes it trinitrotoluene. Here's aspirin or acetylsilic acid. And so we're going to talk about these groups over here, but there it is. There's benzene or a benzene ring. So, and I just mentioned this a second ago. But again, originally they're called aromatic because they're very volatile and they have distinct odors or an aroma. Now, I want to point out there's no rule that says you have to be able to smell it. It's just common that, again, because they're nonpolar, it's a nonpolar component. They will generally have weaker London dispersion forces, making it, the more volatile it is, the more likely it will vaporize, the more likely it will enter your nose, trigger your olfactory response, and then you smell it. But I put here's a couple smells. So here's a smell of strawberries. If you've ever experienced mothballs, this is naphthalene. It's two benzene groups linked together. Here's a chemical you found in coffee. Here's vanilla, or the main component. It's in vanilla extract. Here in a flowery smell. And here's bacon. We love bacon. At least me and my family love bacon. I bet you like bacon. This is also showing, instead of normal benzene, it's a heterocyclic. It's a heterocycle, meaning there's, instead of just carbon in the ring, it has nitrogen or some other. So again, if you ever take a real class on organic chemistry, it doesn't technically have to be a ring to be aromatic, but one common theme, there's always going to be these alternating double bonds. And so there can be linear things that are aromatic, so not rings, but we're not going to go over the rule. Now, the rule that talks about how to spot it, we talked about the guy last semester. His name was Auguste Kekul, and you have to look up the Kekul rule. So, and that's Kekul with a K, and I don't remember the rest of how to spell it. Kekule. That sounds right. I don't know if that's Kekule, and it's kind of a funny E because he was German, and I don't know how to use those other weird letters. Again, this is kind of a recap, but again, anytime you have an aromatic ring, there's resonance, and it increases the stability. So if we were going to talk about chemical reactions, that's one thing chemists look out for is, can it produce aromaticity? Because then it's going to be greatly stabilizing. Now, for us, the main things we need to know is, hey, what if we're just wanting to name something? If it's the main component, we call it a benzyl group. So here, this is nitrobenzene. So benzene with a nitro group. And since there's not multiple things on the ring, we don't actually have to specify whether it's we would call this 1-nitrobenzene. If there was something here, then it'd be like 1, 2, and whatever the other group is. Now, if you have something bigger, and you would consider the benzyl ring, the benzene ring, a substituent, then it's called a phenyl group. So if we were to look at this, you might say the longest chain is this 4 carbons in a row, which I know 4 is greater than the 6, is less than the 6 here. And the rules get kind of murky, and we're not going to get too technical, but let's call this butene. 1, 2, 3, 4. And this is 2-butene. Or actually starting here, 1, 2, 3, 4. Then this would be trans-2-phenyl. So this whole benzene group is on the second carbon, and it would be called 2-phenyl. So whether you hear benzyl or phenyl, it's always referring to this type of 6-carbon alternating double bond ring. And to point out that this CH3 is bigger than the unseen hydrogen, and this aromatic ring is bigger than this carbon. If the larger things are on opposite sides of the double bond, then we would call it trans. Here's a nice video you should watch. Again, if we were to study the amino acids, we would see that 3 of the amino acids have an aromatic group. There is tyrosine, which has a phenol group. There's phenylalanine, which is literally just a benzene ring. And then there is, what's it called? Tryptophan. And tryptophan has a few other things on it, but yeah, 3 different aromatic groups. Chemistry in action. This is just some facts. You should watch this video. I've showed a video like it, but it's more fire or methane that gets trapped under ice, and then you put a flame to it and it burns, and that's fun. I'm gonna skip past that. So this brings us to functional groups. Functional groups are it's like the dressing, like the extra dressing that at a salad bar. So you might say that the lettuce is if lettuce is the main component of your salad, then functional groups are the dressing and all the toppings. You know, whether you want tomatoes or carrots or cheese or olives. I don't put olives on my salads. Olives are gross. But ultimately, what is on the alkyl? If we're what's on an aromatic hydrocarbon or a aliphatic hydrocarbon, there's all different sorts of functional groups that could be placed on them, and they are going to give them drastically different properties. So this is a small table of them. I'm going to jump past it. Here's a larger table. And so there's a couple dozen different functional groups. And what they all have in common is it's a small number of atoms. So this could be a single double bond oxygen, or it could be here's a double bond oxygen with a nitrogen group, or just a single oxygen, or just a single halogen group. And so each one of these will change the characteristics, both physical and chemical properties of a normal hydrocarbon. Now, some of the ones we've already talked about. There's alkenes, alkynes, so double bonds. Here it says an arene for the benzene group, but then yeah, there's sulfurs and some that have double bonds and triple. We talked about some of these, but there's a bunch of different functional groups, but they all will change the name and they will give them different properties. So we're going to cover about 10 of these. Even what we're going to cover, I think, what are the most common 10, but there's probably another dozen we won't talk about, but that's okay because they're not as common. Or if you ever come across them, you can just Google, you can just do some home research. So probably by far the most common is the hydroxyl functional group. Now, it's called a hydroxyl substituent, but if a hydrocarbon has a hydroxyl group, we call it an alcohol. Again, when you hear alcohol, you think drinking alcohol, like the adult beverage, or that found in gasoline, or you think isopropanol, like in rubbing alcohol. And what they all have in common is a hydroxyl group. So, and that's simply adding an oxygen. So this is showing 2 carbons and 6 hydrogens, which without the oxygen would be ethane. But because there's an oxygen kind of stuck in there, it makes it ethanol. Now, what's most notable about adding this, it can now form hydrogen bonds, which is a game changer. So hydrogen bonds, we said, are the strongest of the intermolecular forces. Again, they're not as strong as a covalent bond, but they're way stronger than other dipole-dipole and especially London dispersion forces. And so hydrogen bonds, it's going to do a lot. Now, even though there's a hydrogen on an oxygen, we'll look later at functional groups that are acidic. These ones are not acidic. These hydrogen does not come off. Now, if we went back to a chapter on equilibrium, we could look up some KHs, KAs, and see, well, technically like 1 in a trillion do come off, but we're just going to say no, they're not. 3 of the 20 amino acids have hydroxyl groups. That includes, let me think off the top of my head, there's threonine, there is I can't think of it. Phenol. Phenol has an aromatic group and then an OH hydroxyl on top of it, and then serine. Serine's the third. So that means if you're studying biochemistry and you see an amino acid that has serine, threonine, or phenol, you're like, oh, it's got something that can form hydrogen bonds. And as you've probably already guessed, the suffix will be nol. So ethanol, propanol, phenol. This is, you can find this in antifreeze, ethylene glycol. Again, so methanol, and some of these you might hear said differently, like methyl alcohol, ethyl alcohol, isopropyl alcohol. But again, the IUPAC approved name is methanol, ethanol, and 2-propanol. Now, 2-propanol is also called isopropanol, and that's saying if you normally said propanol, you would assume the hydroxyl substituent is on carbon 1. But if it's iso, notice how you have 3 carbons and it's branched off the OH, and you could say this is an isopropyl group, and that's why it's commonly called isopropyl alcohol. Again, there's phenol. So some fun things: methanol, again, also called wood alcohol; ethanol, drinking alcohol; rubbing alcohol. Phenol is the active ingredient in, I can't remember what it's called. It's like a throat spray. It has a analgesic effect, which means it kind of numbs and reduces the pain of a sore throat. Again, this is the stuff in antifreeze, which if you ever accidentally drink antifreeze, there's a good chance you might die, and we don't want to do that. So don't drink antifreeze. Phenol, this is if you've ever heard of the plastic BPA, this is the plastic that can get converted and polymerized into bisphenol A. I don't know what does the A stand for? Hold on, I'm gonna Google. Okay, I'm back. You might not have known I left because I just hit pause. The A is literally just A, because there's also PBB and PBC, but back in like the early 2000s, like 80% of all the plastics that were used in food, used in containers, not used in food, but tons and tons of BPA was used. But then there were some articles that said, hey, it might be linked to some negative effects. And then everyone jumped on this bandwagon saying BPA is bad for you. And nowadays you'll see things advertised as BPA free. And do people know that BPA is bad for you? Not necessarily, but they know that why not get something else that doesn't have BPA? And so you'll find other plastics that are almost identical to this with one modification, but then that's just a marketing tool, is to say, oh, it doesn't have this. And people are like, I bet that's a good thing. Anyway, I won't talk about that. Oh, going back to antifreeze. Yeah, if you drink it, you'll die, because the same enzyme that converts ethanol, it's called alcohol dehydrogenase, will act on this to produce oxalic acid, which will crystallize in your kidneys and then lead to kidney failure and then death. Ooh, I like that. That's fun. I mean, don't drink it. Now, again, here's some reactions you don't have to know. So to produce ethanol, you probably already know this. You've probably heard of fermentation. Got some biochemistry in there where you allow different enzymes in things like brewer's yeast to break down disaccharides, monosaccharides, and it will, again, produce ethanol. Now, you could also go and buy ethanol at Lowe's or some other store, and it won't be in the beverage aisle, like Lowe's doesn't have one, but it's technically chemically the same. However, it's made with much harsher conditions involving sulfuric acid. And for that reason, it's not considered safe. Not that you could necessarily consider this type safe, but they will normally also include a small amount of methanol, which they then call it denatured ethanol, and they do that so that people can't buy it to drink, because if you drink it, you'll then die. So don't buy ethanol from Lowe's and then think you're going to have a party with it. Again, I mentioned this a second ago, alcohol dehydrogenase. So upon consumption, this breaks it down into another functional group we're going to talk about called an aldehyde. This is acetaldehyde. And if you've ever heard of people having some negative effects the morning after, this is probably why. So acetaldehyde builds up and causes you to kind of flush, body temperatures elevates, there's inflammation, and it's not pleasant. Now, your body gets rid of this with another enzyme called acetaldehyde dehydrogenase and converts it to just vinegar, acetic acid. However, maybe you have a problem. Maybe you drink too much, and so doctors prescribe you antabuse. And antabuse is an inhibitor of this enzyme. And so what happens is if you drink and it makes acetaldehyde, it prevents your body from breaking it down, and you have extra negative effects. And so that's just some fun facts. Hey, look, there's some other functional groups we're going to be talking about pretty soon. Now, after alcohol, alcohols have an oxygen with are linked to a hydrogen on one side. Ethers have again, the R stands for just the rest, but specifically not hydrogen. So some other carbon. So if you have carbons on both sides of an oxygen, then this is an ether. So here's diethyl ether. So oxygen with two carbon groups on the side. But again, if it doesn't have a hydrogen, it is not it is not an alcohol. So what's one of the differences, because it's lacking a hydrogen, it doesn't hydrogen bond. So ethers are generally much more volatile, and working with them in a lab, you generally have to be a little more cautious because they're all of these things are flammable, but because this one's even more volatile, makes it extra dangerous. Now, in terms of reactions, you can combine an ether, or you can combine two alcohols to make an ether. Now, we are going to look at a few what are called condensation reactions in the next video, but we'll get to that and we'll see how you can make it. And then for nomenclature, you'll either see the word ether, like diethyl ether, or oxy. So oxy refers to an ether. So here's methoxyethane. So these two carbons are the ethane. Here's a methyl group, and there is the oxy. So methoxyethane. If we look at polysaccharides, which are pretty much any type of sugar, complex carbohydrate, they all have ether linkages. So this is a sucrose, and there's a sucrose. Glucose and glucose. And sugars have tons and tons of hydroxyl groups. Sugars are pretty much polyalcohols. But the way they link together is by they take two alcohols, they link together, and they make an ether. So sucrose has an ether link between glucose and fructose, and maltose, and let's see what other. There's a bunch of them. But if it ends in ose and it's not a monosaccharide, then it's linked together by ethers. A very common polymer that gets made for drugs and cosmetics is polyethylene glycol, which is, again, ethylene glycol, but then polymerized, and you have ether linkages over and over and over and over. Here we have a crown ether. And so it's a bunch of, every two carbons, there's another ether linking it together. And again, if you look in biology, similar to the polysaccharides, here in lignin, also found in cell walls, what's linking these aromatic groups, you can see carbon, oxygen, carbon, carbon, oxygen. There's just lots of ether groups. Aldehydes and ketones. Now, what these are both going to have in common is a carbonyl group. And a carbonyl specifically has a carbon double bonded to an oxygen. But the way to tell which type it is, you have to look at then what's attached to that carbon. If one of them is a hydrogen and the other is carbon, it's an aldehyde, and it'll have the suffix -al. If both of these are carbon, it is known as a ketone and will end in -one. So back to aldehyde, here is cinnamaldehyde, the main component in cinnamon or cinnamon flavor. And again, the real name is 2E3-phenyl-prop-2-enol. Again, Al tells you there's this aldehyde. And in this case, it's counting prop 1, 2, 3, 4. So not 4, 1, 2, 3. So this is considered the main chain right here. Hold on. So this is 1, 2, 3. I don't like using that. Or did I still do that backwards? No. So we have 2-ene, which tells us we have this double bond on the 2-en, and then the Al tells us that it has an aldehyde, and the 3-phenyl tells us that there's a benzyl group on the third carbon, this entire thing. The 2E tells us about it tells us about it has an optical isomer, and so but we're not going to worry too much about that, because then things get complicated. We don't want to get complicated. Okay, so let me get rid of that. We also, oh, and there's the aldehyde group. Yay. Formaldehyde. So this is the smallest aldehyde, also known as methanal, but typically known as formaldehyde. This is what's in embalming fluid. So if you go over to Mr. Pate's room, you can find some of this stuff where like pig heads and feet are preserved in it, and that's pretty gross. Here is acetaldehyde, also called ethanol. And then here's just a kind of a side note. This is also a really, really, really common extra group I want to point out, the acetyl group. And this is when you have, instead of a longer chain or even hydrogen, if there is specifically just one carbon next to a carbonyl group, it is known as acetyl. Just like this is acetaldehyde. So here's the aldehyde, and by saying acetyl, it's one carbon. Again, you already know acetic acid. Well, acetic acid has exactly one carbon on both sides. So that's just more fun fact. It doesn't actually fit right here, but I guess I decided to leave it there. Here's fructose. So again, most sugars, they can exist in multiple forms. We're not going to actually talk about their straight chain versus ring form, but here we have this carbon oxygen with two carbons on both sides, making it a ketone. Here is acinophenone, again, on a phenyl ring, and here is the ketone. Here's acetone, so nail polish remover. Again, there's the ketone. So the properties of the ketones will have different properties than the aldehydes, but they both have a carbonyl. Again, you do make sure you know this is a carbonyl, because there's two more functional groups we're going to talk about that will have this carbonyl. So aldehydes and ketones both have them, but depending on whether one of them is a hydrogen or neither, there's a bell, will signify. Oh, you should watch this video, because I'm not going to do right now because I want to get through these. The carboxylic acid. Now, carboxylic acids have a carbonyl, and they have a hydroxyl. So this is one we've actually already talked about. So in previous chapters, I've said, well, we have things like nitric acid and sulfuric acid and hydrochloric acid, and they were all ionic. They all looked like ionic compounds, but since they gave off hydrogen ions, they were acids. And then I said, well, what if it's organic? How could it be an acid? And I told you it's going to have a carboxyl group. And so abbreviated COOH. And seen here, here's the carbonyl, and then here's the hydroxyl group. So a carboxylic acid is like an alcohol and a ketone that have been fused together. And what's probably most significant about them is they are acidic. So this hydrogen can come off. And as we've said before, they're all technically weak acids. They don't come off completely. They all have an associated Ka, but still that's going to be important. They're going to have low pKa's, which mean they remember the pKa is the negative log of the Ka, and the lower the value, the more likely they're going to end up deprotonated. And in terms of naming them, they end in ic acid, like carboxylic acid. All the amino acids have at least one carboxylic acid, and two of them have two carboxylic acids. But we'll briefly talk about how proteins link together, and they're going to be, one half of it is going to have to be a carboxylic acid. So here's a bunch of fun examples. Formic acid, the smallest, acetic acid, butyric acid, benzoic has that benzene group. Glycine is the smallest amino acid. Oxalic acid is the stuff that diethylene glycol can get converted to and crystallize out in your kidneys and kill you. And then here's citric acid. So you know that one. It is triprotic. Okay, but what they all have in common is the ability to give away hydrogen ions. Again, when you hear the word fatty acid, now fats have long carbon-carbon chains, but they each have a single carboxylic group at the end, making it slightly acidic. Now, and here's a little bit of the reactivity. So when we say they have low pKa's, they're able to donate this hydrogen. And one of the reasons this is going to talk, this slide talks about why are they acidic? We're hydroxyl. So if you got rid of the carbonyl, why isn't that acidic? Well, by adding the carbonyl, look what happens. You could draw this, or you could draw this. There is technically resonance between this deprotonated side. So anytime something can promote a product with resonance, it is going to make it more likely. So if you get rid of this carbonyl group, then when oxygen gets rid of hydrogen, it doesn't have resonance and it's not as likely. But again, carboxylic acids, they are acidic because the products are stabilized by resonance. So again, here's phenol. It has a pKa of 10. Again, the alcohols have very high pKa's. So when they give away an electron, here's what you got, and that's it. So they're not acidic. The only way you would get phenol to deprotonate is if you were to bring it above pH 10, which would be in a very basic condition, but we're not normally working in those conditions. Okay, the next functional group is the ester. And esters are what you get when an alcohol reacts with a carboxylic acid. All of your lipids have ester linkages. Your fat, I think I'll have a slide on that in a little bit, have ester linkages. So here's a carbon. So it's like a carbonyl and an ether linked together. So it's an oxygen. If this R was a hydrogen, it would be a carboxylic acid. But if the chain continues with carbons in both directions, then it is an ester. So compared to ethers, these are more easily broken. They're more easily hydrolyzable, which means you can add water to them, and it comes down to they're more polar. The suffix, we'll look at some examples, often will have OH or literally just the word ester. In these lipids, there's our ester linkages. So technically, these two long chains stopping right, if we were to break this, right, these right here, we would have two fatty acids with carboxylic acids and alcohols on the other on this side. But when they're still linked, they are esters. Probably the most well-known attribute of esters is they tend to have pleasant fruity aromas. If you were to start looking at all the examples of what gives certain fruits their smell, then it's esters. So in pineapples, it's propyl hexanoate, where prop means 3. So on this side, there's 1, 2, 3 carbons. Then here's the ester with 1, 2, 3, 4, 5, 6 carbons, making it hexanoate. Strawberries have benzyl acetate. So again, here's the benzyl group, and this is an acetate group, but this is the ester. In grapes, methyl anthrolate. So this is actually a larger group that has the anthranolate, but then here is, so this is not the IUPAC name, don't worry about that, but here is an ester. Apples, here's pentyl pentanoate. Again, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So penta. Bananas have pentyl acetate. So this is the acetate group, and 1, 2, 3, 4, 5 is penta. If we were actually here, I have a lab where we were going to make pentyl acetate. And you make it by taking, there's another bell. You take, if you were to cut it right here, okay, oh, sure. If you were to cut it here, this is acetic acid, and on the other side, there'd be an OH, so this would have an OH. So if you take acetic acid and 1, 2, 3, 4, 5, and pentane, and you heat them with a little bit of sulfuric acid, you get them to condense to pentyl acetate. And so we were going to make it and then smell it and be like, oh, yep, that smells like bananas. But we're not going to, because thanks, coronavirus. Amines. So amines do not have a carbonyl, unlike aldehydes, ketones, and carboxylic acids. Amines specifically have nitrogen. And where carboxylic acids are acidic, amines are basic. Now, there's a variety of amines. Here, this is glutamine. It's called a primary amine because it has two hydrogens and one lone pair. This is one of the amino acids, and this thing can be either neutral or positive. Now, normally, if we said draw an amine, we would expect the neutral form that looks like NH2. But what makes them special, what makes them basic, is the fact that they can take on an extra hydrogen, an extra proton. So remember, proton acceptors are bases. So look right here, NH2. Are you watching? Looking right there. Bam. NH3 plus. So it can take on an extra proton, and that is the opposite of an acid, which donates a proton. Now, if you look over here, I want you to notice, hey, look, there's NH2. Is that an amine? The answer is no. And the reason why is because of this carbonyl. We'll get to this one next, but the moment you put a carbonyl next to an amine, a nitrogen group, it is no longer considered an amine. This one is not basic. So while this nitrogen can accept a proton, that one will not. And then these keep popping up. This is just showing primary amine, secondary, tertiary. I mentioned these terms with carbon the other day, with how many hydrogens it has connected to it. It's not the most important thing in the world. Here's a porphyrin ring. Both your hemoglobin that bind iron, as well as chlorophyll that binds magnesium in plants, have this porphyrin ring, which what actually holds on to the iron, or in chlorophyll, it holds on to magnesium, are these nitrogen groups. And so there's two secondary amines, and then here are two tertiary amines. That's what the 3 is for tertiary. Aniline is a fun common solvent that can be used to make a whole bunch of things, from like rocket fuel, different dyes. By itself, it smells like rotting fish, so that's kind of fun. Now, amines have nitrogen with no carbonyl next to it. So amine, not amine. If you throw a carbonyl next to it, like what you're seeing here, this is what's called an amide or an amide. And again, the biggest difference is these are not basic. These do not accept protons. They too, again, they have this resonance contribution. So again, here's glutamine again. So this is the same figure. So this is not an amine. This is an amide, but this is the amide. Now, you don't have to like draw this out, but these are very stable because there are two resonance structures that can be drawn. And by far the most common place you hear of amides or amides is in a peptide bond. So what makes a protein is linking different amino acids. And every single amino acid has both a carboxylic acid group and an amine group. And so when these things react, they react to form an amide group. So sometimes they're called amide linkages or amide bond or peptide bond. But between every amino acid in a protein chain, you have carbonyl nitrogen. And again, this nitrogen is not basic like the amine. And lastly, we have the thiol. This is specifically sulfur. So you hear thiol, just instantly think, oh, it's a sulfur group. And sulfur has very similar chemistry to oxygen because it has 6 valence electrons, typically 1 or 2 non-bonding pairs, but the bonds are notably weaker because sulfur is a bigger atom. Thiols generally are known to have kind of some bad smells, and they're just also really common. Here's vitamin B1, thiamine. It's got sulfur. Here's thioacetone. I think we watched this video your sophomore year, but 5 of the world's most dangerous chemicals, it will come up. One of them will be thioacetone, not because it's dangerous, but because it is terribly smelly. And it talks about 2 accounts where this stuff was accidentally released, and it cleared an entire town. Like an entire town had to be evacuated because how bad the whole city smelled when like one vial of this stuff busted. It is also important in holding protein structures together. So proteins are a linear polymer of amino acids, but then there are 2 specifically called, there's 2 amino acids that have sulfur, but one of them, known as cysteine, has a free sulfur group, and it will link together across a protein. And it's kind of like, taping different parts of the protein together so it stays nice and folded. Again, going back to the bad smells, here are 3 different thiols that you can find in skunk spray that make them smell bad. So yeah. Okay, and so these are the 10. I think there's 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The 10 functional groups. There's honestly probably about a dozen more, but these are by far the most common. So what I'd like you to do is pause the video and just practice. See if you can spot where these 10 are. So go ahead, do that. Go ahead, pause. I'll just be right here sitting, thinking about lunch. Oh, I should go get lunch. And I'll put up the solutions. I guess you could just pull it up in the notes. Okay, you don't know this, but I just went to the lunchroom and ate, let's see, some chili and sun chips and roasted potatoes. And Miss Pam's still doing it up real nice over there. For you, this might have only been like 5 seconds. But I'm back now. And so to finish up this video, again, let's practice. And this is when I would call on you and put you on the spot in class and say, hey, can someone find me an amine, or what we'd call an amino group? And I might say, Brianna, where's an amine? And she would be all like, well, Dr. Gleason, that porphyrin ring that I see in heme A, it has 4 amino groups because they're nitrogens and they don't have any carbonyls attached to them. And then I might say, okay, Gideon, can you tell me where an amide is? And he would look, and he'd look, and then he'd say, oh, wait, down there, look, because it looks like an amino group because it's a nitrogen, but there's a carbonyl next to it, making it an amide. And then I'd say, Kellen, where's a hydroxyl, which would make it an alcohol again, and that's an OH, an OH group, but not next to a carbonyl. And this maltose, it's got a whole bunch of them. There's 1, 2, 3, 4, 5, 6, 7, 8. And then Grace, either Grace can answer, where's an aldehyde? Okay, well, aldehydes have a carbonyl. So like there's a carbonyl, but next to it needs to be a hydrogen. And so there's an aldehyde. And then I'd say, other Grace, whichever one didn't answer, where's an aromatic group, or also a phenyl or benzyl group? And you'd be like, it's still in cinnamaldehyde right there. Okay, Tessie, where's the ester? And she's going to say, well, it's got to have a carbonyl and next to an oxygen, but then the carbon has to continue. So this is not the ester. We're going to look, and we're looking. Oh, there it is. Good job, Tessie. Then Claire, how about you? Where's it at, Claire? Where's the ether? And then, okay, so it needs to have oxygen, but just bonded to 2 carbons. So not that one, and not that one. Oh, there's one right between these 2 in maltose. And there's another one, and there's another one. So there's 3 right there. And then Cole, where's the carboxylic acid? And Cole's going to be like, well, obviously right up here where there's a carbonyl and there's a hydroxyl group. And so together it makes it a carboxylic acid. And then Aubrey, where's our ketone? Okay, well, now we need a carbonyl without a hydrogen next to it, without a hydroxyl, without an oxygen. It needs to have carbon on both sides. And look, there it is. Good job, Aubrey. And at this point, I don't remember who I've called on. I know there's 10 here and there's 10 people in the class. So I would just hope that the last person I haven't called on would just go ahead and say, oh, yeah, the thiol, it's got a sulfur. So I'm sorry, person I can't think of right now. It's not that I've forgotten you. It's just I don't remember who I've specifically called on. I know there's Grace and Aubrey, Brianna, Tessie, Claire, Cole, Kellen, Grace, Gideon, Emily. I don't know which ones I called on or which ones I did. So anyway, here they are. Again, this is how it looks in your notes, I'm pretty sure. But here it all is nice color coded. So be sure you can spot these different functional groups. Oh, look, here's another one for you. So I don't think I don't have the solutions in the notes on this one. Here's the big long name for this thing. But I want you to practice. I put all 10 functional groups in this one molecule. So try to spot where are the 10 functional groups. And then when we pick up on the next video, we'll start with this and point them all out. So anyway, have a super fantastic day. Yeah, okay.